Timer stopped. Reset, start. Okay. So, people understand countable and uncountable infinities. So, let's talk about the halting problem. So one way of sort of talking about limits of computation is to say there are uncountably many functions. There have to be, that reals are not countably infinite. I think, so they're definitely infinite. So if they were finite, they would, okay, now I'm not sure, like if there's a definition of uncountably infinite that's more complicated than just not countably, infinite and not countably infinite. Proves that reals are not countably infinite. Yes, okay, so there are more infinities. You get into this Aleph stuff. I think, so from what I remember, the continuum hypothesis is asking if there's an infinity between the infinity of the countable infinity and the infinity of the reals, and it's independent of like Zermelo-Frankel set theory and blah blah blah. I don't know. I think it's just if they're not countably infinite, if they're infinite, not countably infinite, they're uncountably infinite. Not sure. I would have to, don't quote me on that. I did also, I posted an announcement that I made a mistake in the stuff about fine-grained reductions. I was saying the strong exponential time hypothesis was that 3-sat or something like that. And it's not 3-sat. We have algorithms for 3-sat that run in better than 2 to the n time. In 2 to the n minus some constant epsilon, those exist. It's actually for k-sat. So for there exists some k where you can't do that. So I got it right. But going, pushing on, so functions are uncountably infinite, and Turing machines are countably. So that already sort of establishes they're uncomputable functions, but that's not a constructive proof. So can we find something that cannot be computed? And we're going to do this with a diagonalization with mathy judo with proof by contradiction. So assume that, so the halting problem says, does a Turing machine, so this is why Turing invented Turing machines, so that he had a model of computation that people would accept, and then if you could show that this couldn't do something. I think everyone is going to accept C as a model of computation. Like if you can do it in C, then it's computable. If you can't do it in C, then it definitely looks, we're going to take that as, we're going to agree that C is, if you can't do it in C, then it's not possible. And C is Turing complete, so actually this is sort of the same, but it's just because C is more familiar, at least to me. So I'm going to use the blue marker because the black marker, even the good black marker, is starting to run out. How would you do this? So you want the halting problem, says you're given the C halting problem, says given some, just checking, is this recording? Yeah. Given some program written in C, does it stop? Okay, it doesn't, let's forget. Yes, okay, so that's the trick. But for people who haven't seen it, so you want a program that now it can handle import or not, but let's, oh yeah, you have to, So you have to make it taken in. So halting problem. So given a C program, P, and an input X, does P halt on X? Okay? So this is, I mean, you can write a program that says, okay, read the input. If the input is 5, drop it into an infinite loop. So this would actually be quite nice for compilers to be able to do this. So you can get rid of the input if you want, but I think we want the input in a couple of minutes. So the idea is, so could you do this? Could you write a program like this? And the answer is no. Why? Well, if you could write a program like this, so suppose P, given a program P, suppose there exists a program that solves this. So suppose there exists a program H that solves the halting problem. Solves the halting problem. Okay? Then we can write a program H prime that, so I'm going to do this in a couple of steps. That halts, that given P and X, that, comma, halts if P on X halts, and otherwise drops. Now, I'm going to change this later into an infinite loop. Okay? We could do this, right? We would write, so, void H prime, given, so given a string P, given a string X, so if H Px, so if P on X halts, return, else for I, well, forever, do this stuff, loop, just loop, do nothing, and if. Right? So this is here, here. Okay, that's easy. I've just written H prime. Wait, oh, there's stuff going on. nothing has changed in the chat. Okay, so that's fine. So if P on X, if P on X halts, then this halts. If P on X doesn't halt, then this doesn't halt. Okay. But now we're going to do the tricky thing. So halts if P on X. So this is if H says P of X halts, and otherwise it. So now we're going to put in here what happens if it doesn't halt and otherwise drops into an infinite loop. So now if H says P of X, okay, I have to get this right. If not HP of X, then it halts. And otherwise it doesn't, right? So, okay, so now we have a program which we're going to call H double prime, that if it's given a program and it's a program and an input, if the program halts on the input, then H double prime doesn't halt, and if the program doesn't halt in the input, then H prime halts. So this is like, it's a bit like I am lying, okay? So now we're just going to change it again, where this is going to take only one argument, and it's going to take only one program. It's going to take, the argument is the program, and if the program halts on itself, then this, if the program doesn't halt on itself, then this will halt. And if the program does halt on itself, then this will not halt. A program is a string, right? Remember I had char pointer, char pointer. So now you have a program which, given any other program, says, okay, if program P, given itself, and it makes sense to give programs themselves. For example, have people taken compilers? One of the ways that you test a compiler, when you first write a compiler, you can't compile it with itself. So you do this manually. You compile it manually. This is how they did the C compiler, for example. You figure out how the C compiler would compile itself. You do that manually, and then to test whether your compiler is working, you compile it with itself and see if you get the same code back. So, for example, compilers are programs that can be run on themselves. So, look, here is the code where if there exists a program that says H that solves the halting problem, then I can write this. I can have a program that takes a string, asks if that string as a program halts on itself. If it doesn't, this will halt. This is actually, okay, so this would be H double prime, but H triple prime. If it doesn't halt on itself, then this halts, and if it does, then this doesn't halt. Okay. Then what does H prime do on H prime? H double prime do on H double prime. So it's gonna take a description of itself, which is just here, right? Because we can include H, this H as a subroutine, right? So down here we have this H as a subroutine. So it takes this whole description, which is a string, and it's given this as a string, as an argument, and it calls H, and then if H says that it will halt, then it doesn't, and if H says it doesn't halt, then it does. So we've reached a contradiction. So the halting problem is not computable. There is no algorithm that does this, that tells you, given a C program P and an input X, does P halt on X? Are people happy with that? Like, could you, if I told you there existed this program, could you build this H double prime? Maybe H double prime was a bad example. It was a bad name. Okay, so write a program Q. That given P and X halts if so now we've got halts if now we're given P halts if P doesn't halt and drops into an infinite loop. So this is not a hard program to write, right? Like it's right here. It's a small voice width. Okay, so that's the halting problem. So that's, I mean, even though we're showing that something is harder than like NP complete, this one was actually done in the 30s. It was like, okay, there are limits to computation. So this is a fairly easy thing to see. So let's, so that's the first diagonalization. The second diagonalization that we're going to see is Kolmogorov complexity. Has anybody heard of Kolmogorov complexity? Sorry, I get that wrong. So what does this prove? It proves, so since we get a contradiction here, right, so what does Q do on Q? If it halts, then H is wrong. Because H says Q on Q. If H says Q on Q halts, then Q on Q doesn't halt. And if H says Q on Q doesn't halt, then Q on Q does halt. So we've reached a contradiction. So that means that there doesn't exist a program H that solves this halting problem. So it's not actually, like I said, it's like this. You're building something. You're assuming it's a diagonalization because you're assuming H exists, and then you're using it as a subroutine to fool it, to reach the contradiction. Oh, this is like, so it's for Konkol, this is like, it's the same effect as while true. Do nothing. This will just never stop. So if you do 4 semicolon semicolon, it's saying, wow, don't do anything to initialize it, don't do anything as your test, and don't do anything, don't increment I or something like that. It will just, that for loop will just do nothing forever. Okay, so it's an infinite loop. Okay, so, and then you can do a lot of, yay, reductions by, for example, it's not possible to tell if a certain line, in general, it's not possible to tell if a program will ever execute a certain line. Right? And you can show that it's not possible. You're given the code for the program and somebody says, are there any conditions in which it will reach this? Well, you can reduce the halting problem to that. How? Well, you just say, okay, well, I take a program and I want to tell if it halts anywhere where it would say halt, I'm going to redirect it to say, okay, go to that line. So it halts if it executes that line, and then you put something in where you say, okay, I'm only going to reach this line if it halts. And so now you can give it to your compiler says, well, I can tell if a line is executed, and you give it and you say, okay, is this line ever executed? And that's the only line that says halt. It's equivalent to saying, does this program halt? So there are lots of things in compilers where it turns out that compilers cannot do something because it would mean if they could do that, then you could solve the halting problem. So I think there's, I haven't checked this, but like from 20 years ago, I think it's called Rice's theorem. So the Kolmogorov complexity is also something we would like to do, and it's also incomputable. So let's do Kolmogorov complexity, and then this is the end of the course. Well, there'll be a review. But, so this is not bad, I think. This isn't exactly C. I would have to have curly braces here and here and stuff like that. But it's like C. It's basically C. Okay, so Kolmogorov complexity. The Kolmogorov complexity of a string is the length of the smallest program that outputs that string. Okay, so Kolmogorov. Length, so let's say it's the length in bytes of the shortest C program that outputs X and stops. Okay, so I like C, so this is going to be a C program. Notice that one of the nice things about Kolmogorov complexity is, if you think about it, the Kolmogorov complexity doesn't really matter. Not much changes if you switch programming languages. Why? Because, for example, if you say, oh, I don't like C, I like Java. And you say, okay, but Travis is talking about the complexity of this thing in C. And you want to write in Java. Then what you could do is just write a Java compiler in C.